All right, so hey, as the next topic, we'll be talking about grading visibility of distortion in heat-treated coated glass. And this will be presented by Eric Hegstrom from LightSentry. Eric has 35 years of experience of software development. He's been in the glass industry for a long, long time, and he has built an extensive knowledge about production processes, quality assurance, testing. So very eager to hear, Eric, what you have to present.
All right,
Go ahead.
Thank you for your introduction, Riku, and welcome everyone for joining us here. My name is Eric Hegstrom. I am the Vice President of Technology at LightSentry and Soft Solutions. We have plants in the United States and in Austria. I'm going to give a quick presentation. I know Riku mentioned distortion. I'm going to touch a lot on anisotropy to begin with, and we're going to do I think we had some questions last time. I don't know if anyone attended my talk 2 years ago, but there were some questions on coatings and how they affected anisotropy. And so I thought it was kind of good to go through the whole process of what actually causes anisotropy in tempered and heat strengthened glass and how coatings affect that. And we'll also touch on distortion and then go into the actual grading objectionability of the patterns and then talk a little bit about equipment. And of course, why tempered glass? We all know this. We're in a tempered symposium, strength, safety, thermal shock. You want small pieces of glass. And what are two of the problems we often see in tempered glass are these two independent properties that occur. Anisotropy, this ghostly light and dark images that we see, the light and dark areas we'll see on glass when there's polarized light available, and what we call optical distortion, which is reflected distortion, when the glass is treated like a mirror and it's not flat. We see these objectionable patterns in reflection. And so, just a quick overview of the tempering process. Once again, you all know this. First, the glass must be washed. In the US, there's always washers before the tempering line, and I know in Europe a lot of the times you expect the glass to come clean, but if it's not clean, it's going to possibly stain in the heat treatment process. Then of course it goes into the furnace, and you've got like two competing goals. You need to get it up above the transition temperature to relieve all the stress, so you need to get it hot enough to relieve all that internal stress, but you don't want it to be too hot for too long, otherwise the glass tends to warp and gets that objectionable distortion in reflection. And then of course the glass must be cooled. In the case of fully tempered glass, it's quenched, it's cooled very quickly on the outside, a little slower in heat strengthened. And we've all seen these pictures. Well, I hope we have. I mean, we've seen these stress profile pictures. And what happens is during the rapid cooling of the glass, the outer surfaces cool first, forming a solid core, and the inner part of the glass will try to shrink, but now it can't because it's held tight by the outer core. So we set up this tensile and compressive layers. And also during the quench, any optical distortion, any deviation from flatness is locked into the glass. So that's going to be there until hopefully it's never installed at your customer's site. And when you talk about anisotropy, it's important to talk about polarized light because it's all about polarized light. When you want to analyze the light based on polarization, we break it into two separate components, two separate oscillations. We have what's called P is red, and it oscillates in like the screen. Blue oscillates out of the screen. And the important thing to remember, a non-metallic surface such as glass or water will reflect the P light, but allow S to pass. And this is exactly what you see if you go fishing and put your polarized sunglasses on. This is the glare from the top of the glass that your polarized sunglasses will cut out so you can see what's going on. You can see the fish. You can see the bottom of the ocean. And these layers of tension and compression are what causes anisotropy. So if we look at glass that's just annealed glass, totally stress relieved, and we're just going to look at the P polarization because that's the part that's interesting, it'll pass right through the glass, no anisotropy present. But what happens, and I was trying to find a picture of this, but I could not find a picture of how what happens to the molecules during the tempering process. There is actually a direction-dependent deformation at the molecular level of the glass, and these local anisotropic deformation causes the polarization of light to rotate differently as transverses through the thickness of the glass. In a theoretically perfectly balanced tempering situation where the outside compression and the inner tensile layer is perfectly balanced, the P polarization goes through, it rotates going in a lot, and then it rotates the other way and it rotates out, but by the time it hits the back surface, it's just like it came in and it transmits through just like if the glass was fully stress-relieved float glass. Now, in reality, there are many areas where there's an imbalance in this tensile and compressive layer, and we have a rotation, but by the time it hits the bottom surface, in the worst case, it's rotated the half wavelength of that light and now becomes S and bounces off that back surface. So you get this bright reflection. And this is kind of an example of what you see in the real world, where it's perfectly balanced, you see a nice smooth area, and in the areas where there's a stress imbalance, you see these bright ghostly reflections. And these reflections, as we saw before, are coming off this second surface, this back surface of the glass. And that's something important to remember, because the anisotropy and the rotation of the light happens in the body of the glass. But what you're seeing, the effect you're seeing, is the reflection off that far surface. So there are actually two things going on there. I mean, if the far surface was a theoretically perfect anti-reflective coating, you would see nothing in any case. But typically the coatings, have a certain level of reflectivity, and that affects how visible a certain level of anisotropy is. And the question is, can we quantify that effect? Is there a way to analyze the coating and quantify how much of an effect the coating has on the visibility of the anisotropy? And this is some work done by Saint-Gobain over many years. The coating and the glass is analyzed in a photospectrometer at two different polarizations in both transmission and reflection, and they're able to sum up all the internal reflections and come up with basically a color difference in what you're seeing between the highly reflective areas and the not reflective areas. And this color difference is what I would say the level of visibility of the anisotropy. And this is quantified using the CIDE 2000, or as we call it, lab color, which is a perceptual model of color. So differences in this perceptual model are tested to be an actual difference in perception. So using that, and we won't go into it, you can read in the paper, there's a lot of stuff online. I mean, we've got 12 minutes left, so we can't really talk in detail. But the interesting part is there was a significant amount of what we call psychophysical testing, where they took 40 glass samples at different levels of tempering strengths and 8 different coatings, and they were able to verify that this theoretical analytical model of predicting the visibility of the coatings matched well with observations made by humans. And now we'll talk a little bit about distortion. I won't go a lot into it, just to talk about it's typically measured in diopters, and what we're really looking at is the curvature of the glass. As the diopters get larger, the glass is more curved, and that makes your reflected image look different. There's certainly a lot on there. You can look at my previous presentation on YouTube if you want. And what's important to know is that optical distortion comes in many flavors. There's your classic one-dimensional roll wave and edge lift that we've been measuring for years with gauges, or with many things where we just look at how an image gets bigger or taller in just one direction. But there's a lot more optical distortions we care about these days. There's, pocket distortion where it looks like it's been hammered. There's picture framing where the edges lift up, and there's some very subtle bistabilities. And there's one that we've looked at and we've seen a lot popping up recently, and it's called center kink. It's where you have optical distortion running in the opposite, running parallel to this, running into the direction of the transport. And it's a bit insidious, because this is something we presented at a building envelope conference, I think 2 years ago, and this ended up being a forensic study. And this part, as it came out of the oven, I mean, we're all familiar with the classic zebra board, which you can really see roll wave on. It looked perfect. And it ended up going to the site. But the interesting part is, as you rotated it around 90 degrees, that is the only time you were able to see this fine find distortion in the direction of travel. And this is what I wanted to point out, and this was exacerbated by the coating. On the left, you see the actual part that was in the field, and you can see this is probably a very expensive problem for somebody because it was installed at the site, and they see this large distortion going up and down. I mean, and you can actually, I don't know if you can actually see the roll wave in there too much. And next to it is a simulation on a much darker coating. And so it's simple with distortion. The distortion, the visibility distortion is directly related to the reflectivity of the coating. It really doesn't involve a lot of colors and a lot of internal reflections. It's just the reflectivity of the coating. And this is an actual measurement out of a machine. So you can see clearly that there's a very light, I mean, what I would call great, very low level roll wave going that way, but this very obvious level of center kink distortion. And now we move on to, we talk about the global score. Historically, we've just measured how much anisotropy it is 90% of the glass under a certain number of nanometers. We've looked at distortion in the same way, is 80% of the glass under 100 millidiopters. But, you know, human vision is highly accurate in perceiving, you know, higher frequencies. I think, and this goes back into the 60s, they did a lot of studies and they found that pattern perception peaked around 4 cycles per degree. So there's some very well-known studies on what level of patterns are objectionable. And the question is, can we develop a global score using what we know from the coding, the sigma QM coding calculation we showed earlier, the visibility of the coding, and the contrast analysis. This is another work that Saint-Gobain did, the research group did a long time ago. And they presented a method for computing the contrast pattern by looking at the contrast, the luminescence, and the background, and also looking at the spatial frequency of the pattern and tie into that the observer distance. They were able to come up with a general global score. And they further refined this by adding local filtering based on a certain distance from the pattern, so patterns that were only visible when you were close were filtered out. And this gave this along with the evaluation of the coding gave an actual method to generate a global score, which modeled the actual human perception of the objectionability of the pattern in the glass. And some further psychophysical testing with humans showed, and all the dots are what human observed and how they rated it compared to the global score, showed a very good correlation between those two. And what this all means is that we now have everything necessary for a complete product agnostic grading system called the global score. So architects, building owners, fabricators, consultants can communicate their expectations on what a building should look like. And this hopefully in the future will lower the necessity for doing mock-ups, and it'll allow people to have a very clear understanding of what they expect to see and a clear way to actually measure it and quantify it so they're being delivered what they're told to deliver it. But the beauty is, we at Light Sentry have been working with this technology for a while, and the machines to make all the necessary quality control measurements and do this in your factory are now available today. Now, if we talk about what you use to implement this, these are example of some of these ASTM compliant equipment for measuring distortion and anisotropy. This is our flagship unit, the Osprey Light Sentry. Over 500 of those have been out in the field over the last 20 years. Our newer systems, the line scanner from our other company, Soft Solution, that does anisotropy, and our new Osprey 25, which builds on the older technology with a lot more new features. And I do want to talk a little bit about how the distortion is measured. There's something what we call Distortion 360. As I talked about earlier, in the old days, it was all about roll wave and edge lift. I mean, that's all we cared about, roll wave and edge lift, measuring in one dimension, how the glass gets bigger and smaller, how the images get bigger and smaller only in the dimension on the conveyor. But this is an example of a part running under one of our systems. We look at the reflection of all these little white circles, and as you can see, the leading edge here, the circles are expanded in this direction, and in the body of the glass where it has much less distortion, they're rounder. And the beauty of this is it uses all the intensity levels to generate a subpixel calculation, and it gives you very good data in all directions, in all 360 directions, all 360 degrees. And one question I often used to get is like, well, these circles, they're not very dense. We don't have very good coverage of the glass. But one thing I like to show is, as the glass travels under there, it is imaged 5 times, and that's, as it goes under, you get one set of circles, and the circles interlace. So as it traverses under there, each part of the glass is measured 5 times, so you get a very dense coverage of these optical distortion measurements on the glass. And once again, we have what we call all edge. We measure out to all the edges, not, because glass typically has more than just lead and trail that we've talked about in the past. You care about what's going on the left and right edges, or if it's a round top, what's going on around the whole circle. And you care about the distortion in multiple dimensions, not just in roller wave direction. And this kind of is an example of how those circles would distort. In roller wave, they just get, taller and shorter. When you're dealing with hammer distortion, it's more of a spherical distortion where the circles get larger and smaller in 2 dimensions. When we're talking about center kink, this insidious problem we saw before that didn't show up on the zebra board, the circles get wider and narrower. And then there's, in real life, there's many sorts of mixtures where the circles can distort in all sorts of different ways. So it's very important to be able to measure this distortion in 360 degrees. And also our systems, the Light Center Osprey uses global shutter cameras. They take a snapshot in 0.5 millisecond, so in 1/2000th of a second, they capture the glass in one place, so there's no stitching going on, so all the measurements are made with a clear snapshot of the glass. So if there is any sort of susceptibility to conveyor transport issues, slippage between conveyors, out of height rollers, things that happen in real factories, but not maybe in your lab system, that is minimized. And since the system's taking a snapshot, these kinds of motions happen between those snapshots. So it allows you a very unparalleled vibration insensitivity. And on the final note, when we talked about coatings, it's important to be able to enter these coatings into the system, to know what these coatings on the glass are. And you have a couple options for that. One, you can count on a operator to enter those numbers manually. And, well, I don't need to explain why that sometimes can fail. It's important. Or you can get the numbers directly from our ERP system that can send them down. And that usually works, but we know in a glass factory, sometimes parts break, occasionally glass breaks, or there's a remake that needs to get put in there, so it's possibility to get the wrong coating. So it's very helpful to have an online sensor such as this that'll measure the coatings on the glass and analyze that in real life time. And also, it's very important to have 100% audibility to be able to share the results with the customer, and to have automated reports and alarms, so you always have all this data at your fingertips. You can get cloud-based reports you can share with your customer. You get push notifications if production is not going well. So it's just great to have all that stuff, and I think I've been through it all here. And as I say, please reach out to us if you have any questions. We cover both the EU and the United States. Thank you very much.